Welcome. My name is Kay Taylor. I'm VP of Education here at the Rocket Center. So glad to see you here. I hope your conference is progressing well. I hope it's meeting your expectations. Hope you're learning a lot. I have to kind of shake my head to try and get all of this information to settle. It's a little overwhelming. But we're thrilled to have Dr. Prasana Balaprakash here with us. He's going to be talking about how AI is changing the process of scientific discovery. Dr. Balaprakash is the Director of AI Programs and Distinguished R&D Scientist at Oak Ridge National Laboratory outside of Knoxville. He directs laboratory research, applications of AI and machine learning to solve problems of national importance. His research interests span artificial intelligence, machine learning, optimization, and high-performance computing. So we are so thrilled to have him with us as part of this inaugural conference on AI. Buckle your seatbelts. I'm going to turn it over and let Dr. Balaprakash speak for himself. We will have time for Q&A at the end, so hold your thoughts and we'll ask questions. Dr. Balaprakash, thank you, sir.
Thank you so much for the great intro, and thank you for inviting me. And this is a fantastic opportunity that I see to sort of say what we are doing at Oak Ridge National Lab in the space of AI for scientific discovery. It is really, really great to be here. So the theme of the workshop is how to make AI work for you, right? So I sort of structured my talk around that theme. AI is really changing the way that we do science, but I'm going to put more emphasis on secure, trustworthy, and energy-efficient AI, which is really making a big impact in the way that we do scientific discovery. Oak Ridge National Lab, so if you're new, if you haven't heard about Department of Energy, our Department of Energy labs, these are the set of like a network of labs that were born out of Manhattan Project. And if you have seen Oppenheimer, that is the movie, that's the birth, that's the starting point of all the national labs. It started for research in atomic bombs, but later it sort of moved towards national needs about how to advance our research, our technology in quest of various types of energy. Oak Ridge National Lab has a very rich history in AI. So this is a sort of a timeline of the AI history over the years. We started around not we as a field, AI, 1940 to 1970, the dawn of AI and the birth of Turing tests. And then 1980s, navigating through the AI winter, we survived. 1990s, new era of AI, machine learning, data-driven machine learning, early prototypes, early algorithms came into existence. 2000, the onset of deep learning, generative AI, again, early methods. And 2020, we have generative AI, and we are already talking about expanding the frontiers and having conversation around ethical considerations. It came a long way. And this is Oak Ridge National Lab's history in this timeline. The first project in AI was started in 1979. These are three bright minds that thought about how AI could potentially change the way that we can do science. They were talking about various types of autonomous methods, AI to drive experiments, AI to accelerate scientific discovery. And in 1981, this brilliant mind already started thinking about how AI is going to come and how AI is going to change the various aspects of scientific discovery. So this is, they already started developing at the time infrastructure for spectroscopy, environmental management, of course, nuclear fuel reprocessing and things related to that. In 1983, a lot of work on robotics. So people were trying to see how to bring AI to robots that can operate in a semi-autonomous way. And these are primarily based on expert-based systems. 1991, automated machines. So these are robots, the robots that were designed to do obstacle avoidance and environmental monitoring, in particular nuclear waste and so on and so forth. This is pretty dangerous, so thinking about how can we build robots that can do the job. 2017, we had Summit. The time when it debuted, it was the fastest supercomputer in the world. And at that time, it was a machine that built with IBM, collaboration with IBM and NVIDIA. People were trying to use GPUs, or graphical processing units, that is the powerhouse of AI at the time. And NVIDIA, until that point of time, is known for gaming. Their hardware is known for gaming. Around that time, DOE, Oak Ridge National Lab, and NVIDIA came together and said, oh, we can use these type of hardwares to do high-performance computing, which means we can use this sort of compute power that we use for games to solve challenging problems, scientific problems. We made a bet, and Summit came into existence. And several libraries, several software ecosystems and libraries that were developed during that time, trying to make multiplication of two numbers faster. So that's really the workhorse of every AI workload that we could think of. If we make faster this particular operation to multiply two numbers, we are good. In fact, we are doing amazing things with those fundamental operations. And we got this mission in 2017 and started doing AI at scale on supercomputers. And then there is a proliferation of GPUs after that everywhere. So this particular mission played a major role in NVIDIA's roadmap. And now NVIDIA is not anymore a gaming company. It's an AI company. And it's very hard to buy a DGX machine, right? We have to stand in line. I don't know how much the wait line now. After doing that, we did something else. In 2023, we built this new supercomputer called Frontier. When it debuted, it was the fastest supercomputer. It can perform exa operations per second, more than one exa operations per second. What does it mean? It's 1 followed by 18 zeros. That many floating point operations or multiplications that this machine can do. If you start writing 1 followed by 18 zeros, I counted this morning, it will take 10 seconds. Within that 10 seconds, this machine can do 10 exaflops, right? So within 10 seconds, it can perform 10 exaflops. And in terms of mixed precision, so we always do, not full precision. In particular for AI, we can reduce the precision in which these machines operate, and we can reach 10 exaflops per second. Think about it, right? 10 to the power of 18 operations per second. Okay. The point of going from 2017 Machine Summit to Frontier is also is motivated by the fact that, okay, yeah, we want to reach this exascale, right? So we want to do 10 to the power of 18 operations per second. That was the target that we were chasing. And we can potentially do that with this type of machine, like buy more, that's the data center model, right? Buy more GPUs, buy more NVIDIA GPUs, stack them one after the other. If we have done that in 2018, 2019 timeframe, we needed a nuclear reactor next to the machine to power this machine, right? So we took a challenge and said, we want to reduce the power consumption. Now, this machine is on the order of 10 megawatts, right? It's still a big number, But compared to the energy consumption of Summit 2017 machine, this is several orders of magnitude smaller, right? So we wanted to build this machine in a much more power efficient and in a responsible way, as opposed to buying more machine and just stack them up. That's why it's second. Number two on the Green 500, which is a benchmark used to measure the power efficiency of the machine. So it's not only the only supercomputer that is available for open science, the fastest one on the planet, but also is the second most energy efficient supercomputer on the planet. We can do amazing things with that machine. It's such kind of power that we have, and we can do lot of advanced AI research on this machine, which is in fact powering much of our AI research. I will talk about that. AI is fundamentally changing the way that we do science in Oak Ridge National Lab, across DOE complex, across the nation, and across the world. Here are a few examples from our lab, right? I want to emphasize few. There are more than 100 different exemplars, and we can keep on talking about this. And these examples sort of illustrate or give you a flavor of what type of research that we do. Spallation neutron source is a user facility where we use a strong neutron beam, project that neutron beam, or pass the neutron beam into a material and understand how this material structure looks like. Often this material structure, from those material structure, we can determine the properties of the material. This is a fundamental characterization process in material discovery. Whenever we come up with a new material, we want to characterize that. What is happening inside? We are not talking about just material from the outside. We are talking about material structure at the atomic level or at the subatomic level, right? So neutron beam is neutral, so it can, it is not deflected within this material, so it can go through and sort of, get diffraction pattern where we can look at this material from a very detailed perspective. The amount of data that is produced by this user facility, specifically spallation neutron source, it's in the order of terabytes. We cannot afford to do the business as usual here. We want to do near real-time data analysis, that is the data coming out from this experiment, so that we can inform what is the best experiment to do the next cycle, the next minute, the next day, and so on and so forth. We are using AI to accelerate that process. Otherwise, think about it. You generate terabytes of data, take it to the lab, analyze that, and that is 6 months to 1 year cycle. Now we are thinking about reducing that 1 year cycle to 1 day. What it means for scientific discovery? Tremendous. Right? So this is tremendously impactful. In manufacturing demonstration facility, we are using AI and robots to improve various aspects of manufacturing process, looking at the 3D printing while the 3D printing is in process, can we characterize that material and use that information to modify the actions of the robot, right? So those are exciting things that we are doing at the manufacturing demonstration facility. At the Center of Structural Molecular Biology, we use AI to analyze plant phenotype data and understand how these plants are going to evolve, are going to sustain, are going to stay healthy in drought conditions. In the light of climate change, this is very, very important. This is my favorite, Oak Ridge Leadership Computing Facility, which I'm closely connected to. We are using supercomputers to simulate climate, to simulate fusion reactors, to simulate stars, universe. We study them. And this process takes 6 months, 1 year, sometimes even more. And now we are using AI to reduce the computational expense of these complex simulations. The weather simulation, which was taking 6 months before, now we can do it in a day. because we can approximate the computationally expensive part of the traditional simulation using AI and use that AI to accelerate the simulation. The classical weather simulation, you are looking at 30 ensembles, and those ensembles are the ones that give us reasonable prediction. Now we are talking about doing thousands of ensembles, thanks to AI. Cyber science research facility is another area where we are using AI to improve the cyber defense. Oak Ridge is the only Office of Science lab that has both science and national security, and this is a huge advantage for us because whatever happening in the national security side on the cybersecurity, we are bringing that for science side. When we talk about deploying models, how to protect these models, how to protect data from data poisoning, how to protect models from adversarial attacks and things like that. When we are putting a model in an experimental facility, AI to drive a multi-million-dollar experimental facility, we need to be absolutely sure. We cannot leave anything for granted. We have to protect the model. We have to protect the actions of those models. We cannot allow a cyber attack to come and hijack that model and take over that experimental facility. So there's a lot at stake. In high-flux isotope reactor, we are using AI to improve the isotope productions. Isotopes are used in various applications, starting from medicine all the way up to fueling rockets. So we are finding ways to improve the isotope production using AI. These are great, but there are many grand challenges we need to solve. If we are really looking into ways to bring this AI into production, into scientific discovery, into acceleration of scientific discovery. As documented in this Nature paper, AI will transform science. There is no doubt about it. But the question is how we are going to tame it. And it is not surprising that the White House put an executive order a few months back on this very, very important subject. This is not about doing AI for X, Y, and Z. This is about doing safe, secure, and trustworthy AI for the use of for applications. This is one of the questions that was asked in the last session, right? So what is government doing? What is happening on this front? So government is putting executive order, putting guidelines about guardrails, about safe, secure, and trustworthy AI, how to do it properly. And if there is one country who can stand up and do this, it's the United States. Because we care about this. This is not an easy task. Again, this was discussed in Andrew's session as well. This is a very, very challenging task. The AI itself faces several paradoxes, right? So some of them I list here. Often AI is easy to demo, right? So we can quickly write code and in a Jupyter notebook and take that and say, oh, here is my little model doing prediction. But it's very, very hard to put that into production. It's really challenging. There are several deployment challenges. Things don't work when you put in production. They don't work in the way that you expect to work. So this is not a software engineering problem. There are fundamental algorithmic problems in the way that we approach AI. Hard problems are easy, and easy problems are hard, particularly for AI. We are at the point of civilization where we can synthesize everything that is known to us, that is available in the literature, in a single AI model. That's amazing, right? Whatever that is known to us in the scientific literature, we can take that, train a large language model, and that language model knows everything, right? That's an amazing capability. But at the same time, we cannot make a robot to tie a shoelace, right? It's a super easy problem for us. It's a very, very hard problem for AI. So we need to understand the strengths and limitations of the AI models that we are developing. There is ever-growing open research problems. Andrew talked about version 1, version 2, right? So the more complex AI model that we build, more powerful model that we build, the more problems that are arising out of these models. And we are not talking about ethics as much as we do now compared to like 5 years back. It doesn't mean that we didn't have AI. We had AI. But now we are building really powerful models. And those models are not solving all the problems, but also they are opening up new problems. Very, very challenging problems. Humans still remain a roadblock when it comes for evaluating these models, right? For bias, for misuse, for dual use, and so on and so forth. We still rely on human experts to provide guidance, stakeholders who can understand this technology to provide guidance. And the proliferation of AI models and the kind of things that these models are doing across many application domains present challenges. There are unique challenges associated with cyber-physical systems. There's one thing about ChatGPT running in a server, and you are interacting, and you get the results, and you see the results. Yeah, this makes sense, this doesn't make sense. It's a completely different ball game when you take an AI model and allow the model to do something with a cyber-physical system. That's why self-driving car is still something that we are chasing, right? Because it's an AI model or AI systems or self-driving system that is put into real world where you have actions and those actions have consequences. So we have to figure out how to do this. So the challenge is multifold when you put AI systems into cyber-physical world. There is a fundamental paradox with AI efficiency. Why we want to build AI systems? Because we want to be efficient in everything we do. We want to do this much faster, or we want to increase the profit, or we want to get 10x productivity compared to what a human can do, and so on and so forth. But there is a fundamental paradox for that. It's Goodhart's law. Too much of efficiency makes everything worse, right? And we have seen many examples around it, right? So there is a well-aligned phase when developing AI systems. Let's say you have a system and you say, okay, here is my high-level goal. I want to maximize user engagement in my platform. Okay, how can I do that? I go and design an AI algorithm to do that. Okay, then how do you do that? You convert that high-level goal into a set of mathematical equations that AI model can optimize, and then you train. Great. And what you see is your overarching goal and the AI system goal sort of aligns. And then at some point, what happens if you keep on over-optimizing that system? Things start deviating, or you will have even consequences that you didn't expect as part of your design. And this is often the case, right? So yes, I want to increase the user engagement on my platform, which eventually results in addiction for the users, right? We cannot keep on doing this way of like building systems without taking into account the other metrics. We cannot go to the Congress and say, hey, I made a mistake, right? Like our CEO of a popular social platform did, right? So it's very important to look at the system from a holistic perspective, looking at all the objectives. And this is more important and becoming more and more crucial for scientific discovery, right? So we can go and design a new material for application X, how to prevent someone from using the same system for weapons, right? So alignment is a generic term that sort of says, okay, how can we design systems that align with multiple goals? Human goals, system goals, societal goals, and so on and so forth. So it's important to think about this as a part of the design as opposed to, okay, let's go and build the most powerful AI system and then think about what are the legal complications, what are the consequences, what are the dual uses. I think we as a community, scientific community in particular, there's a lot of responsibility on this one, right? So how to think about these things and bring that as a part of the design process rather than going and building the most complex model and then think about the consequences as a later thought, as an afterthought. So here is a little example for misalignment. So this is a simple AI system that was trained to play this game, Coast Runner, right? And the overall objective of that system is to maximize the number of points, right? So if you're designing an AI agent for playing a game, what will be your objective? Your objective is to maximize the number of points that you gain. And the AI agent learned to do something different. What it is doing is actually aligns with your goal, or the goal of the system, but it is doing something different. It learned to do this dangerous maneuver in the game and keep on doing that in the loop. So if you do this maneuver and then hit these things, you will keep on getting these points. You see there? And it never completed the game, right? Because that was not part of the objective. It was not part of the objective. Keep on increasing the points by doing this dangerous maneuver without completing the game. And this is not just an example for that occurs in games. So this is something that shows what we call physics-informed neural networks. It's an AI model designed for prototypical science problems. So here the science problem is just to predict where two pendulums will go, right? So it's a simple problem, right? Very simple problem. Even for that problem, we have to incorporate known physics into the AI model. So this is one way to align this model, right? Saying that, okay, I know something about the underlying physics. I can bring that as a set of equations, and I can build a model. And what you see here, oops, okay. Anyway, so even for those cases, we see misalignment. Even for the simple cases, AI model can learn the cracks in the either in the game or in the data or in the system that we put in, and try to sort of cheat. And these are not exceptions. We see this more often than not. So alignment is such an important concept, right? So when we start building these type of systems, to ensure that AI systems' goals and behaviors align with science goals, like particular application goals, but also human values and intentions. Capturing these intentions, human intentions and human values, and converting that into a set of mathematical equations that the AI systems can understand, we are just scratching the surface. We have to make a lot of progress on that front. It is important to prevent harmful consequences of AI actions, right? So this is where alignment comes in. And I talked about those challenges, right? So defining these human values and how to convert that is still an open question. For certain applications, we know how to do that. For certain applications, we haven't even started how to do that. And there are many different challenges. It's also made difficult by the fact that it is a continuous effort, right? So we go and build a system and then see what are the unintended consequences. There are unintended consequences that we can sort of guess and try to put guardrails, but then when the system is in production, then you will see different set of consequences, right? So we have to continuously improve the way that we develop these models and put them in deployment. So our objective is often like have effective decision making, predictive analysis, automated operations. So there are many things, right? But there are several obstacles: bias, misuse, lack of understanding, and more importantly, complexity. These models are very complex. It's very hard to understand. And guardrails are important. the guardrails should be part of the design process. And the guardrails here can be ethics, transparency, privacy, fairness, and security, or a mix of this, depending on the context. Quality assurance in AI, that's a very, very big topic. So we know how to do this in classical software development, right? So we have user requirements, and then we can translate that into software, and we have various ways to test the software. But when it comes for AI models, many of the existing traditional software evaluation or software testing fails. So how can we, so the validation part of it is like, how can we build the right AI product? And the verification part of it is building the AI product right. So validation, the validation part includes alignment, user testing, and real-world performance, and then iterating. The verification process is much more involved, where we go for model review and then go for model testing and performance evaluation. And we have to iterate. The challenge is, in particular, in the context of generative AI models. So generative AI models, by definition, they generate new content. We like generative AI because it is generating new content. It's not just imitating what is in the training data, right? This is good, right? It produces hallucination, yes, but it also sparks creativity. In particular for science setting, this is very, very important. So by definition, we are looking for new content. And these new contents are generated at scale. Again, the new content doesn't have a proper mechanism, like how we can validate this new content, right? So that's where the verification process and the validation process are becoming very, very difficult with these models. So the importance, again, ensures models are accurate, reliable, and fair. The challenges include subjectivity, because the way that we evaluate new content changes from one application to another application. For language models, it's fact-checking, right? So, okay, new content generation, is it factual or not? Is it just a made-up thing, right? That means, you know, that has a lot of implications. On the other hand, if we are generating new molecule from the existing drug database for drug discovery, that is good. If that molecule has properties that is amenable, or that can have potential to cure cancer, that is a good thing. So making up new content or hallucination, by definition, it's not bad. It depends on the context. And also the diversity of generated outputs, right? So we are, ChatGPT is only one modality, generating language. You already saw examples from Sora, right? This is about generating videos. We can generate images, text, videos. In science, multiply that complexity by 100. We are talking about point clouds, molecules, time series data, and so on and so forth. So we have a wide range of modalities that we are operating within the science domain. So that means more complexity, and that means we have to make advances in the way that these models are evaluated. Here is the elephant in the room: energy consumption. So generative AI, as you know, is very, very energy consuming effort, to train and also for inference. And the recent estimate is like per year, energy consumption for AI generative model training is equivalent to a year energy consumption of Ireland. And this is continued to grow. And I'm not really surprised that Sam Altman from OpenAI went for this $7 trillion effort to come up with new hardware for AI, right? So he's talking about this, the need for new AI hardware that is needed. Because I have questions about 7 trillion effort, but I think we all can agree, or the scientific community can agree, that the current way of scaling up on GPUs, it has its own limitations. We have to pay a lot of energy cost. And there is also a lot of environmental impact. This little graph shows what we are after. So we are building larger and larger models, but the return or the effectiveness that we get is started diminishing. And on the x-axis, you can see the computations, the billions of floating point operations, and around 10 to the power of 18, the carbon dioxide generated by doing that many operations is equal to the CO2 generated by New York City in 1 month. Right? So that's the environmental impact that we are creating by generating large AI models. There are many other implications, like cost implications, infrastructure strain, and so on and so forth. But this is something that we cannot afford in the way that we are doing things. So I talked about all the challenges, and quickly looking at how we can do this. So this is, how much time I have? 10 minutes? 55, okay, gotcha. Oh, Eastern time. Sorry. Great. So this is overall AI initiative that I lead within the lab. And this has two axes. One is the application axis, that's on AI for scientific discovery and complex systems, AI for experimental facilities, and AI for national security. And foundation axis, where we develop algorithms and methods for secure, trustworthy, and energy efficient AI. The foundations sort of help to make advances in applications, and applications inform what type of foundational methods that we should focus. There are many different challenges, right? So many different challenges that need to be addressed. Many different techniques that can be developed. But these three thrusts that we focus is primarily driven by the scientific and the national security applications that we have. And another way is also to think about this is these are not mutually exclusive. So for certain applications, we need secure and trustworthy AI. And energy efficient AI is a fundamental for all large model exercises, large model training exercises. And we also look into how to do AI at the edge, right? Energy efficient, small models that can operate at the experimental facility, right? So we cannot put supercomputers for each of the experimental facility that we have. So there are many things that we can do at the edge in a much more energy efficient way. But we need security, right? So we don't want that model to be tampered with. So that's where the secure problems, the secure capabilities come in. And alignment is a major theme across all the applications. It's not just about training a model for accuracy. It's about taking into account energy cost, fairness, bias, privacy, and so on and so forth. The first thing I want to focus is on our recent effort on training large models. If you have to pick one capability that's going to fundamentally change the scientific discovery, to accelerate scientific discovery, is training large models on scientific data. And you have heard, like, these models are always measured in terms of, model capabilities are measured in terms of the number of parameters these models have, typically billions of parameters. And recently, if you're talking about billions of parameters, we cannot do that on our laptop. We cannot do that on a single GPU, a single node. We have to use thousands of GPUs, right? And that's where we focus and say, okay, how can we build large model training capabilities on Frontier, right? So Frontier is an AMD machine, it's not an NVIDIA machine. So all the large model training that are done by industry, they are all using NVIDIA GPUs. And all the software ecosystems are all customized for NVIDIA GPUs. But we have AMD GPUs. There's a different software stack. So how can we build this capability and test it on Frontier? And recently we did this exercise. And we scaled models up to trillion parameter. So this model has now trillion parameters. And we use scientific data to train, and so on and so forth. But the key points that I want to make here, this is the first time that such a large model was built on non-NVIDIA hardware in an open science setting. And now we made this recipe available for the scientific community. Typically, this type of effort in the industry, hundreds of software engineers. You know how many OpenAI software engineers work on this, right? We cannot afford that. But we have people who know how to scale these systems. This is the pure brilliance of the people at these big supercomputing facilities, and these are not new for them, right? So they lived with these type of machines for decades, and we use their expertise. We made a recipe to train these type of large models, and we made it as open source. Now, any science person who can get access to this machine can use that capability. This way, we are talking about democratizing this large model training for everyone. Now, this is not a technology only for few major players. This is a technology, if someone has a bright idea, they can write proposal to get into this machine. Any person from academia, right? Now we are making this capability available to the entire community. And that's a game-changing thing. And of course, we are using this capability to train models for our own applications, which I'm going to talk about. But I want to emphasize this transparency, this openness is important for scientific inquiry. Then, this also allows people to start thinking about putting guardrails as a part of the model training, right? If only OpenAI and Meta can train these type of models, if we cannot access that model when it is trained or how it is trained, that's a problem, right? Okay, how we are using this to transform science. I'm going to talk about that next. Material science and material discovery is one of the major application, not only for Oak Ridge, but across Department of Energy. From the moment when you wake up, all the way you come here and go back home, you cannot think of something without the advancement of material discovery. Your car, your phone, your battery, everything we touch and feel is determined by advancements in material discovery. It's such a fundamental area. What is a major problem when we want to find a new material? We are talking about a design space of billions and billions of different material designs, right? Whatever the application. So the number of possible designs, they're talking about millions, trillions, or even more, right? So it's a very, very high combinatorial space, right? Large combinatorial space. And often, what scientists are interested in, okay, so if you've given this huge space, how can I narrow down to few candidates, few promising candidates, so that I can go deep into those promising candidates? So that's the sort of the filter. And traditionally, how this works, using existing knowledge, using a scientist's knowledge, or using existing literature, they come up with few designs, few thousand designs, and they run simulations for each of this design. And each of the simulation, depending on the accuracy, can take weeks to months. And that is a major bottleneck in many, many material discovery process. The same thing with the drug discovery. I'm not going there, but think about this sort of filter. You have a lot of candidates and you want to go and find fewer. And this is a very, very computational expensive process and time-consuming process as well. Now, if we have a model that can predict the properties, AI model that can predict the properties, we can do this in matter of minutes or hours. Because the inference time, once the model is trained, the inference time is cheap, right? So now you can throw in a billion designs into this AI model. It can predict all the billion in microsecond or millisecond and tell you what are the promising candidates, right? And that's where we are using this type of AI models. Using AI models, we train the AI models, which I come next. once the model is trained on a large amount of existing material science data, we can use that model to narrow down promising candidates for different material science discovery applications. And here are a couple of examples. The chromophores, each dot there is a candidate. And the enlarged version of that dot are the candidates that we managed to filter using AI models. And chromophores play a major role in biomedical MRIs, quantum circuits, and so on and so forth. So we identified these promising candidates, handful of them, let's say tens, and then run simulations on this, and then identify the most promising one, and then take it from there. We did the same thing for high entropy alloy. Alloy here, we have more than 5 different ingredients in high entropy alloys, and coming up with the right combination often means it's a very, very computationally expensive process. We cannot do this in real time because to manufacture each alloy candidate, it will take several months. So again, we can use AI model to predict the properties without manufacturing them and identify promising candidates. How we get to this AI model? That's what's shown in this plot. We use Frontier to train a large AI model on material science data. And this data has specific structure. It has a graph structure because materials always have atoms, bonds, and so on and so forth. So AI models that are designed for language are not amenable for this one. So we have to have specialized AI models. But then those AI models on large amount of data, training on large amount of data poses challenges. And that's where Frontier comes in. And what AI model that can be trained on 32 GPUs, it takes 100 hours, but we can significantly reduce the time by using more GPUs in, let's say, in 10 hours. And we can go even more and make it to 1 hour, right? That's the capability that we are talking about. Large amount of data, training the model in an hour, and we optimize these models for Frontier so that it is energy efficient as well. This is another work that we are doing with climate science folks, right? And here we are developing foundation models for climate science. So the traditional way to simulate climate is very large simulation code, which can take several node hours, core hours on big supercomputers. And now we are taking the data from the simulations, from the observations, and training a large foundation model, a large AI model, and looking at, can we use that model to forecast the weather? And we got really good results on that front. And that's what is shown here. So the ground truth is on the lower plot, and the predicted one is on the upper one. And this is a forecast that is done for 7 days, for 72 hours ahead. The key thing here is scaling the AI foundation model. The larger the model, better it is. So this is a foundation model for weather with 1 billion parameters. Okay, and we again scale this training on Frontier and showed that by using Frontier, we can reduce the training time. And we can also achieve a very good scaling efficiency. We can go without scaling efficiency, but then we are losing a lot in terms of power and energy needed for training. So the scaling efficiency is important because in that way, we train these models not only in a shorter period of time, but also in a more energy efficient way. The key takeaway here is instead of running the classical simulations for thousands of node hours, once this model is trained, we can take that model and do 72-hour forecast on the laptop within microsecond. We don't need to run complex simulations for thousands of hours. We are using AI for modeling, optimizing and controlling complex systems. The complex systems, complex engineered systems, are systems that are man-made, where you have several components that are put together in various ways, systematically and non-systematically. And these systems are very, very difficult to model. For example, take power grid. Power grid is a very, very important infrastructure for the nation. But it's also very, very complex. Disturbances happening in one place can propagate across many, many different regions. How to model them, how to optimize them, how to control them. Right? Now AI has a has a tremendous potential to do that. And we are doing some of this for some of the power grids that we have data for. And in particular here, we are looking at what we call physics-informed AI models. So we are bringing in a lot of physics, or a lot of domain knowledge that we have into those models. We cannot afford to throw a lot of data here and say, okay, go and build a model. But more rigorous, robust models need underlying physics. And that's where we are using physics within the AI models. And the related thing that we are also looking at is uncertainty quantification, right? So this is an important point that I want to make. When the AI model makes predictions, we also need to make sure what the model knows and what the model doesn't know. Right? So if the model gives you predictions and say, whoops, my uncertainty around my prediction is too large, don't trust, that's a very good information. So it's the ability of the model to tell what it can predict and what it cannot predict. And that is important in many of the science applications. And here is sort of the prediction uncertainty that was shown. So you inject distribution at time zero, disturbance in time zero, and the disturbance sort of propagates. And we want to predict those disturbances across the power grid, but at the same time, we want to ensure the type of uncertainty that we can get from the model prediction so that we can trust these predictions. To summarize on the large model training part, I want to say, the DOE labs, particular Oak Ridge, we are on to something much, much bigger to train foundation AI models for science. So foundation models are models where we look at large amount of scientific data across multiple domains and train one or few models that can synthesize all the information and then use that model for various types of downstream tasks. In some sense, the ChatGPT is a foundation model. You have a base model that is then taken and fine-tuned on various types of tasks. We are doing something similar for scientific data. And DOE labs are the largest producer of scientific data in the world. We have so many user facilities, so many experiments, and we have generated so much data, and we are generating even more data with our facility upgrades. And we are in a unique position to do this, thanks to our supercomputing capabilities. The one point I want to make here, how often you see Nobel Prize winners going from one field to another field and sort of transferring the knowledge from the field to a new field and make remarkable inventions. Now, in a lifetime, a human can be an expert in probably 2-3 scientific areas, right? Now we are talking about a capability where this model can look at the knowledge across multiple scientific domains, hundreds of scientific domains. I can't wait what this model can give us in terms of scientific discovery. I'm an optimist in this case. Yes, we had the previous session more on the pessimism, but I can't wait to see how these type of models can allow us to find a new drug, to find new material, to address our climate change, to find materials that can allow us to store energy in the battery for much longer period of time. Right? That's the science impact that we are talking about. Think about hundreds of scientists' brains connected to each other and now helping scientists from one domain, right? That's the capability. I can't wait to see what these things can do as we move forward. So, at the same time, we have to look at the trustworthy aspects of these AI models as well. So this is the foundation area that we are focusing on. We are focusing on developing uncertainty quantification techniques, validation verification, explainability and interpretability, and privacy. So I will talk about some of the examples. Some of this also related to the previous session, questions on explainability. So uncertainty quantification is fundamental for whatever science we do, whatever AI models that we do. We need to have uncertainty as the base. Without uncertainty, we don't even look at the model predictions. The first question we ask is, yes, you are giving predictions. What is the uncertainty around the prediction? Right? Because the uncertainty will tell us whether to trust the prediction or not. And it can help us to potentially solve several challenges related to hallucinations, interpretability, and what the model predictions and where it is, and why it is making those predictions, and so on and so forth. So we are developing foundational algorithmic capabilities that can span across multiple science domains. And we have applied that to natural science, grid systems, material science, and I showed the example of the power grid and so on and so forth. Here is another use case for uncertainty and how this is accelerating our science. This is what's shown here. So we have to do this material characterization, and we take a quick sample around that material, and we have a model that can be trained with that data. And now what we do is, using the model uncertainty, we can decide where to sample next. Essentially, if you ask the model, where is the region that you are very uncertain, and say, these are the regions that I'm uncertain, then we can go and sample the data from that particular region and give that to the model, retrain the model, and ask the same question. So it's a classical design of experiment strategy, but 10x improvement on that, right? Now, having a model with uncertainty allows us to do really sophisticated design of experiments. And we have shown that this resulted in 2x productivity. Previously, it's like, okay, we had to do things at random and then see how it goes, and then probably, we have to either oversample the material. And remember, each probe can take several minutes or sometimes hours. And now, instead of doing 100 probes, right, we can do it with 50 probes. And that means reducing the experiment's time from 1 week to 3.5 days. 1 month to half a month, right? So that's the sort of productivity, and that's the sort of thing that we get out of automating experiments, and automation of experiments need uncertainty as one of the base. The safe AI, again, this is about building models with various metrics taking those metrics into account. Accuracy is only one part of it, right? So if you go and read AI papers, there's a lot of AI papers on accuracy. Our model is beating this model. Like OpenAI coming and saying a statement, okay, our model on this particular benchmark is better than, which is an important thing. Don't take me wrong. But accuracy is only one part of the story. With respect to alignment, right? So we need to look at fairness, and fairness means different things for different applications. Privacy, right? Privacy is not an afterthought. We have to build models that can protect privacy of the data while training, not like afterthought. Transparency. Again, this is another conversation we had in the morning. Do we need a transparent model? For science, absolutely. Absolutely. Prediction is only one part of the story. You give a prediction to a scientist, like, oh, this material is predicting this property, this material has this property, and the AI model is saying that it's not going to make the cut. On the other hand, you say, okay, my accuracy is 80%, but I can tell you why this property is like this, and you can associate that to a material structure. That can result in a Nobel Prize, right? That's the impact that we are talking about when it comes for transparency and explainability in science. I understand in business world things could be different, but we do care a lot about explainability and transparency of the model. And energy efficiency is obviously another major impact, right? So how can we train these models? We cannot, in some sense, we are not competing with anyone to be the best model ever. So we are making foundational advancements in the way that we can train the model. We have the luxury to rethink how to train these models in a much more responsible and energy efficient way. So we are looking into ways to automate this model training, not just for accuracy, but also taking into account multiple metrics. This is called automated machine learning, and now we have Frontier at our disposal. We can do this in a much more efficient and systematic way. So this is one example where this is for a fusion disruption detection. And what you see here is 3 objectives. One is, of course, accuracy. The other one on the x-axis is the batch inference time. And y-axis is, the z-axis is the number of parameters. And those 2, lower the better. And the validation R-square, higher the better. Because you want to be accurate, but at the same time, you want to generate smaller models. You want to design smaller models. And the inference time should be smaller because you want to reduce the energy consumption during inference as well, right? So this is the automated search that is run on Frontier. And all it takes is just click a button, submit a job, go home. Within an hour, we have generated thousands of models, right? With different trade-offs. One thing I want you to note is the largest model has the largest accuracy, right? 0.95, the green one, the largest one. So each box size refers to the number of parameters in the model. But look at that red dot here. Here. By sacrificing 1% accuracy, we reduce the number of parameters and the batch inference time by an order of magnitude, or 2 orders of magnitude. Right? So our ability to look at these different objectives and to make a meaningful decision, which model now to choose and to deploy. I would go for the smallest model, because smallest model we can take and explain. It is much more transparent. Yes, we are not as accurate as the largest model ever, but accuracy is a very wrong metric, because it's often based on some specific data that we say, okay, this is the data that we will be using, right? So the point I want to make here is there's more to the other objectives than accuracy. And often we need to look at it from a holistic perspective. And ability to train these models, thousands of them, in a very short period of time, in an energy efficient way, means transformational impact for science and scientific discovery. So this is an explainable AI approach that we have developed for the hydropower generation across US. And particularly we are looking at the factors influencing the hydropower generation. And what we are interested here is to say, like, okay, how the inflow, temperature, and precipitation affects the hydropower generation. So we want to use this as a factor to predict the hydropower generation, but more importantly, prediction is a secondary here. The scientist, the climate scientist, is much more interested in what are the factors, how these factors affect the hydropower generation. And our explainable AI methods are giving that information. It's not about prediction, but it's saying that, okay, day 1, how these things change. On day 2, on linear, how these things change. Linear is a place near Atlanta. And day 3, day 4, day 5, how these things change. Inflow, temperature, and precipitation gives you a sort of, these results give an insight into what is happening inside the model. So explainable AI needs a different class of methods. We cannot just throw in billions of parameters and expect that we can get an explainable prediction. This needs a different type of method, and the objective here is to figure out how these factors influence hydropower generation. Correlation is not causation. In many AI methods, right? Explainability also means correlation. Ice cream shark attack, that example, right? Ice cream sales is highly correlated to shark attack. And if we say that to a policy maker, and if he makes us say, okay, to reduce the shark attack, let's reduce the ice cream production, right? That's not good. That's a wrong thing, right? So that's why it's important to look at what is causing what, and this is super important in science domains, because that means we gain insights. Because these insights are not possible with the classical method. There's classical methods, simulation methods, molecular dynamics, DFT. These are very, very expensive, and we cannot do this at scale. But now with AI methods, we are at the brink of unlocking several mysteries around the materials and material science and so on and so forth. Right? So coming back to the ice cream example, it's the weather, right? So there is a hidden variable that is the weather. And how can we find those kind of hidden variables in scientific experiments? What in material design or in drug design and so on and so forth. And that's where causal methods play a major, major role. This is really the next frontier, right? So we talk about training large models and so on and so forth, but we really need to make advances in causal modeling. And we are working on this, and we are using causal model to understand material properties and use that to design experiments. The same with, we did similar thing with perovskites. It's another type of material. And we use causal modeling to understand various aspects of phase transition in the material. So material, they change phases, and we want to use causal models to understand what is, why these phase changes happen. The question of why, how, this motivates scientists. Prediction is sort of secondary. Yes, we want to have good prediction, but the question of why, what is causing what are the factors influencing this property? Those things are super important for scientific discovery. And I really hope the advances that we make with causal modeling, with explainable models, with interpretability and so on and so forth, sort of trickle down into the industry applications as well. And that's what happened in the past, right? So AI was sort of an academic exercise previously. Now it's everywhere. So we really hope whatever we do for science will help us to address some of the challenging questions that was raised in the last session about guardrails, safety, transparency, stakeholders, policy making, and so on and so forth. So this is another important area that we are working, privacy preservation. So we talked about protecting the privacy of the data. So one idea that we are pursuing is, okay, so here is the data that we want to protect the privacy, right? Instead of training that data, taking the data, training a model, and then think about, how can I protect the privacy of the data after training the model, right? Instead of doing that, that's why I sort of emphasize, we have to think while designing this model. And that's where this approach comes in. So, okay, here is the data that we have, and can we generate a synthetic data that captures essentially the distribution of this data and train on this synthetic data, right? And release a model from the synthetic data. Of course, the question is how far this new synthetic data is from the original distribution. The closer they are, there will be loss in the privacy. The farther they are, there will be loss in the accuracy. There is a trade-off. The point is, we can mathematically guarantee how much privacy we can preserve by measuring these two distributions of the data. And that is great, because for certain applications, you need to have absolute privacy. In those cases, we can take a hit at the accuracy. And that is what we have to tell Andrew and other policymakers. Like, if you are looking for something, there where we need to absolutely, protect the privacy, we have to have this sort of guarantees. Otherwise, don't approve those models, right? On the other hand, we have other applications where we can have, okay, we can protect part of the data and release the other part of the data is not so important. In those cases, it's perfectly fine. Right? So we are doing this for the scientific data, where often scientists, right, say, they generate data and analyze the data, publish a paper, publish their inventions. Now, if we can provide guarantees on the privacy of the data, but then we can learn across hundreds of scientists doing experiments in real time, that is transformational. We can protect the privacy of the data, so which means that their data is not available to anyone, so they cannot make inference about what experiments they are doing. But at the same time, we can use the data from multiple experiments or multiple users and develop a model that can be used again by all of them, right? That is transformational. They don't make the same mistakes. They are collectively making progress, but in a privacy protected way. So we are also using a lot of cybersecurity techniques to protect the models, and Oak Ridge is a very unique place where we have a lot of cybersecurity research that happened in the past and AI for science that are happening. And recently, we are merging these two and say, like, how cybersecurity techniques can help us to protect AI models and what are the risks? So there are two fundamental questions that we are trying to address. What are the threats emanating from AI systems, and what are the threats to the AI systems? And we have recently launched this center called Kaiser. It's a center for AI security research where we are asking these hard questions, right? Okay, given a model, what are the risks, bias, dual use, and so on and so forth associated with this model? How can we automate? How can we do this with Frontier? Because model evaluation is very, very expensive, and it's also needs a lot of resources. How can we do this in an energy efficient way at scale? And bring that to scientific machine learning models. The AI initiative that I lead leverages many different unique capabilities. Adversarial AI from the Kaiser Institute. Intersect is our autonomous lab initiative, where we are automating the design of experiments across the complex. Leadership computing facility plays a major role. It forms the basis for training large foundation models. Scientific user facilities. We have multiple facilities, not only at Oak Ridge, but across the DOE complex. And Citadel is our secure enclave where we can put the data, sensitive data, and we can train model from Frontier supercomputer. So this secure enclave is connected to this supercomputer, and we can do sensitive data model training with Citadel. That I'm almost done, and I would like to take this opportunity to acknowledge the funding agencies. I'm really grateful for Department of Energy, funded my last 5 years with the DOE Early Career Research Program, and SIDAC Institute for Computer Science and Data, where I lead the AI Trust, and the AI Initiative at Oak Ridge, where we are making all these advances and really transforming the way that we do science in the lab. And before coming to Oak Ridge, I was in Chicago, and I spent the first 12, 13 years of my career at Argonne National Lab before coming to Oak Ridge. It is another DOE lab, fantastic place. I'd like to take this opportunity to thank Argonne as well. With that, yeah, thanks for the opportunity. I'm happy to take some questions.
Okay, so you mentioned earlier about how it's hard for computers to pick up on human, like something simple for us, like putting down coffee or something on the floor, right? So if we use like OpenCV or computer vision, should I say, would that make the calculations easier in that perspective? Would the computer pick it up?
With the computer vision, you mean?
Yes.
Yeah, that modality definitely helps, right? So it's a vision modality, and And also we need algorithms that can manipulate robotic arms. And if you look at it, like, I was giving this example, tying a shoelace, it's like fine-grained motion, right? It's difficult. But now there are some advances, right? So people were trying to approach this problem from a more more a system perspective, like how we can do this, motors, controlling motors and so on and so forth. Some of the recent works are amazing. Like they show videos, right? They take videos of human actions and see like how can we learn from that videos.
Well, I was thinking in terms of cars as well. So like, say for instance, somebody turning left whenever a light, comes on or, is given that permission, so.
Yeah, I mean, car driving or autonomous cars are another example, right? So it's rather easy, or relatively easy, to have a self-driving car in a test environment, right? So no other cars, no pedestrians, no crazy things happening on the road. Great, that's why it's easy to demo. Self-driving cars, super easy to demo. It's very, very hard in production because it's all about edge cases. And AI systems often, they are not good at edge cases until and unless you have a good amount of training data, right? And that's where, we have to inject some sort of, domain knowledge and so on and so forth. So those things help. So there are two regimes, right? So one is like abundant data, right? A lot of data. In that case, you don't need to worry about all other things like throw compute, throw data. We can argue about whether it's a right approach or not, but that's working really, really well. And then you have other applications where you don't have a lot of data, right? So almost zero data, which means that if you don't have data, unless and until you have some sort of way to generalize from large models, you are stuck. So that's where you have to bring physics, at least in the science side, right? So in many applications, we don't have a lot of data because data, each data point can be very, very expensive to generate. So we have to bring in domain knowledge, and that works. And sort of like, we can move from there. So it's a sort of a continuum. It's not a binary, like 0 or 1, but it's a continuum, and we have to really understand what are the data that we have, and what are the bias. What are the sort of, ethical issues, bias, and other things that goes into the data. For example, a biased data will produce biased model. There is no other way that you can prevent, unless you know that you detect the data has a bias, and you bring bias detection and bias mitigation techniques as part of your model building exercise, right? If you don't do that, there is no magic that will help you to say, oh, my model will do this, right? So that's why I'm saying in terms of the autonomous cars, yes, multiple modalities help, but also it's about edge cases. It's about, what are the potential things that can go wrong, and we are still seeing, those things, right? So, we'll get there.
I'm in cybersecurity as well. So right now, there's like websites that you can go to, that you can subscribe to, that you can actually build a virtual PC basically, and like or assign a graphics card, a certain graphics card to do, or GPU to do certain encryption, or decrypt, should I say? And which is scary, by the way. But you bring up the point where we can get into the frontier machines and stuff like that. Do you think the frontier PCs would be able to create a better encryption for everybody, or?
That's one of the research that the other side of the lab is doing, both on the national security side, and also we have quantum programs looking at quantum encryption as well, right? So quantum testbeds.
Do you think quantum is the future instead of, I'm not going to say instead of AI, but over AI?
I think I see a future. It's not like quantum. Quantum is going to solve certain classes of problems. And quantum is not a replacement for AI, or AI is not a replacement for quantum, but quantum is really good at, let's say, if you have a molecular dynamics, it's molecular dynamics simulation, by inherently molecular dynamics is a quantum phenomena, right? It's better to simulate that on a quantum computer, which will be a lot more energy efficient rather than classical computers. Similar to what we are doing with AI, right? AI is better suited probably with spiking neural network on analog hardware, because our brain uses like what? Light bulb energy. And we are talking about like megawatts. Right? So we need to make advances in these directions. I totally agree, right? So what is the right set of hardware for right set of models? We are in a very, very interesting times, right? So now we have the ability to look at various types of hardware, various types of methods, and make advancements. So it's not quantum versus AI, it's quantum, AI, neuromorphic, and other related technologies that I see as a future. Because quantum is really good at certain things, and AI is really, really good at certain things. And probably for energy efficiency, we have to look at neuromorphic, cryogenic computing, DNA computing, and DNA storage, and so on and so forth, right? So exciting, exciting times. I can't wait, how this landscape will look like in 5 years.
You had a slide about midway through, I think, about how you were using AI to filter design capabilities and so forth. And it struck me that seemed very similar to what we've been doing in the job market in terms of sifting through resumes, hordes of resumes, and finding applicants. That process has been horrible because I would say you're getting a lot of false positives and a lot of false negatives. You're not finding the really great candidates. You're zeroing in on people who aren't qualified at all. And I just wondered if you're getting kind of the same challenges with the approach, with the design capabilities.
It depends on the application. So we do see a lot of advantages, right? So it's again, we need to have a human at the end of that filter. But here is the thing. We do have models, and those models can produce incorrect results, but our ability to detect those incorrect results, say, with the uncertainty, helps a lot. Saying that, okay, the model will tell, okay, I'm filtering this, but I have a high uncertainty for X, Y, and Z candidate. And those are the candidates we take and run a simulation and give that back to the model and retrain. This very process of retraining the model based on the errors that these models can make, huge difference. That can make a huge difference. Probably in your case, you need to worry about bias and other things, right? So, any model that is, let's say, Amazon did it, right? So Amazon or one of this major company did this resume filtering through AI, and eventually they had to stop it because their previous hiring process had bias, right? It was biasing the selection to certain groups, so they had to stop it and do this, right? So now I think it's semi-automatic. But the point I want to make is that's why any system that is built without transparency or without uncertainty, we tend to risk those kind of things, right? So if the model says, yes, I'm predicting this, but I'm not sure. I'm predicting this because I'm looking at the demography and where this person worked or what the nationality and et cetera, we have much more informed knowledge about that particular system, right? So I think that is important, and that's what we are pushing here. We do the foundation models, we get causality and explainability into those models so that we can go back and say, like, okay, what the model is actually doing and how we can use that to design the next set of experiments to improve the model.
Can you talk about how Frontier has been able to help, or if there are opportunities that have happened with this, smaller academic labs or independent laboratories who are doing materials science, especially insofar as they have to spend money on equipment and materials and you name it, and there's lots of time and energy and care that goes into this. That funding disappears real quick with that in academic settings in particular. Can you talk about how, maybe some examples how Frontier has helped smaller laboratories like this?
Yeah, great question. So there are two ways that we are looking at this. So one is people who are doing large model training. So how can they come with their own data? Let's say they have specific data sets and they want to train a model. We have a software stack that is ready to go, and they can train these large models. They don't need hundreds of software engineers to do this model training. And there is a process to it, right? So the best, these machines, we thought with the exaflop, we will be like, starving for applications. No. The moment we had the exaflop machine, we are oversubscribed. So people always find a way to come up with bigger problems to solve, which is fascinating, right? I think that's why our next target is Zetascale. And we are sure when we go to Zetascale, we will be oversubscribed as well. So the process is we want to look at the applications that are coming and say like, okay, with the best idea wins, right? So because we have limited compute time, which we want to distribute across several people. So best ideas always win. So there's a proposal process. They have to go through it. The best idea wins, irrespective of your affiliation, right? So that way we are making this purely merit-driven. So this is for large model training, right? So large model training for science, and also people who want to understand, I want to improve the efficiency of the large model training with respect to bias, transparency, and so on and so forth. You can do that on Frontier. You don't need big cloud, which is like super expensive. Again, it's merit-based, right? So great. The other thing is we are generating these foundation models from material science data. So that's our next stop. So we are taking large amount of material science data which are available within the lab, within the DOE complex, within the public domain across the world, and generating these foundation models, and then make those foundation models as an open source for the science community. They can take it and then fine-tune it, like what the language models are sort of deployed. Like you can take the large model and fine-tune it for a specific material science application that you have. That's our roadmap. So we want to help the community by releasing the foundation models, but in a responsible way. So we want to take into account the dual use and so on and so forth. But at the same time, our goal really is to release these models for advancing material science and related science.
Yeah, thank you. So one of the slides you brought up earlier with regard to integrating Frontier, you mentioned training a billion or trillion parameter GPT model with only 3,000 GPUs as opposed to the 37,000 allocation. Yeah. What were the limitations or challenges that capped it at 3,000? Because later you talked about a scale efficiency. So why cap it at the 8%? And was it allocation, energy efficiency, something like that?
Yeah, great question. So two challenges. One is, even though Frontier sits in Oak Ridge, it's a national resource. We don't own it. It is for the country. It is for the advancement of science for the entire nation. So we don't own it, and which means that we cannot run things in a way that we want. We do have allocation, but the allocation that we have is sort of limited. If we have to go large runs like what ChatGPT models are trained, we need to get a large amount of allocation. So our goal was to sort of develop this ecosystem, develop this, figure out a way to optimize large model training on Frontier. So that was our goal. So that's why we didn't train on the entire machine, although we are planning to do that with proper allocation as we move forward. I was telling you about releasing the foundation models for science. That is an activity that we are taking up, and we are trying to get allocation like any other. Like we have to write the proposal, and we have to get hours on this machine, and we want to do this. So that's one thing. The second thing is certainly the scalability challenges. So with the 3,000 GPUs, we are already seeing some sort of scaling efficiency drop, which is around 80%. 80% in general is fantastic. But if we keep on doing this, we will probably looking at 50% efficiency or 40% efficiency. Why is that? It's because the fundamental matrix multiplication operations that we have to do is not really optimized for deep learning, for a large model training. So we are still working on that. And the other thing is, what sets apart supercomputers from other computers? Let's say, you can always think about, I have thousands of laptops. Why don't I just connect, right? The thing that sets apart frontier or sort of a class of supercomputers from others is how you connect these machines, right? So interconnect. And the interconnect need to be fast, in particular for AI training. And we do have limitations on Frontier. So think about Frontier was designed before this large model evolution took place. So the interconnect was primarily designed to advance computational science workloads like simulations, climate simulations, fusion simulations, cosmological simulations. At the time, the kind of deep learning workload or AI workload that we had is not as big as what we have now, which means it's a challenge to train large models on Frontier, right? So that's a challenge, but also a research opportunity. Now, this is really pushing us hard to think about scaling, right? Okay, here are the hardware limitations that we have. We cannot just go and train a large model with lower efficiency. That's a big no, right? Because yes, we can do it. If we have a commercial interest, we can do it and release a model, but that's not the point, right? So we want to train a model with energy efficiency in mind, with transparency in mind, and optimization in mind. So given that limitation, now we are fundamentally rethinking the way that we train these models. So that is pushing us hard to invent, right? So that's what we are working on. I'm happy to follow up. So some of these algorithms, right? So the powerhouse behind ChatGPT type models is called transformers, and transformers and GPUs, NVIDIA GPUs, are sort of match made in heaven. It's not like transformers are amazing. It's, we are at a point where, wow, these transformers are so good on GPUs, right? So that's where many things happen. But can we think about different architectures, more energy efficient architectures? And probably you have seen some of the recent works. Recent works in AI means like last 2-3 days, where people are thinking about building linear algorithms or training algorithms with linear complexity rather than quadratic complexity, which is the transformers and other methods have. So there are a lot of new things happening, and also on the hardware front, a lot of new things happening. So we are also exploring other type of architectures, algorithms, hardware. We are working with several startup companies, Cerebras, Samanova, Rain, Neuromorphics, and so on and so forth, to see what class of applications are better suited for particular hardware, and what type of algorithmic changes or algorithmic improvements or algorithmic innovations that we have to do to make this better, and so on and so forth. That's why it's super exciting time, and I can't wait how things will look like for the next in the next 5 years. 5 years is a long time for AI.
So this concludes our session. Thank you so much, Dr. Balaprakash. And thank you for your optimistic view to balance our day.